Hello, everyone, and welcome to Airborne Data Applications for Invasive Species Mapping with NASA's Applied Remote Sensing Training Program, or ARSET. I am your host, Sativa Cruz, and I am a part of ARSET's Ecological Conservation Team. Today, I have the pleasure of welcoming guest trainers Michelle Thornton and Rupesh Shrestha from the Oak Ridge National Laboratory. More about ARSET. The ARSET program was developed to provide accessible, relevant, and cost-free training on remote sensing satellite sensors, methods, and tools. Our trainings cover many topics in areas such as agriculture, climate and resilience, disasters, ecological conservation, health and air quality, water resources, and wildland fires. They are tailored for a variety of audiences for a wide range of experience levels. We offer both online and in-person trainings that are either hosted live or are self-paced. As I mentioned before, our trainings are free and often we offer bilingual options. To increase access, we use open software and data as well as accommodate differing levels of expertise. Visit the ARSET website to learn more. Just a reminder that this is an advanced training, so there are a few prerequisites for effective participation. To attend this training, we require you watch the Biodiversity Applications for Airborne Imaging Systems ARSET webinar, which is linked here. And we also assume that you have some basic Python programming experience. This will allow you to follow along during the demonstration. We've listed some additional ARSET webinars here for your reference. This is a one-part training with 2 time options available. This training will have homework and it's necessary to turn it in order to receive a certificate of completion. It will open today after the training and is due 2 weeks from now on October 14th. Our guest trainers join us from the Oak Ridge National Laboratory. Michelle Thornton is an airborne data lead and Rupesh Shrestha is a remote sensing scientist. We are so grateful to have their expertise to share with us today. I'd like to take a quick moment to also acknowledge the rest of the ecological conservation team who is here supporting the training, as well as many people behind the scenes who are making this webinar possible. Thank you, ARSET family. So if you have any questions throughout this webinar, type them in the questions box and we will address them at the end. Feel free to enter your questions as we go. And we will try to get to all questions during the Q&A, but if we happen not to get to your question, the remainder of the questions will be answered in a Q&A document that will be posted to the training website about a week after the training. So what are we here to learn today? As stated in our learning objectives, this advanced training was designed to introduce participants to how image classification of airborne imaging spectroscopy and labeled field data can be used to map invasive species. We'll provide an opportunity to use a Jupyter notebook to access NASA JPL AVRIS NG data located on the Earth Data Cloud for a spatial and temporal region of interest. Michelle will demonstrate a cloud-based workflow in a provided notebook to classify species using a trained machine learning model for the Greater Cape Floristic region in South Africa. We will end with sharing key considerations for interpreting machine learning end products for invasive species mapping for land management decisions. With that, I will pass it to Michelle to get us started on spinning up our virtual environment for the demonstration. I will be back shortly to share some background information. Thank you.
Thanks, Sativa. Really appreciate that introduction. So I'm Michelle Thornton, and I'm at the Oak Ridge National Lab, DAC, one of NASA's data centers. And I want to give a little introduction into the NASA Earth Data Cloud, and I also want to give participants the time to spin up a managed environment in which we're going to run the Jupyter notebook that I'm going to be walking through. It does take a minute to spin up that notebook, so we're going to have participants do that now, and when the tutorial exercise comes along, we anticipate that everybody will be able to participate live. So first, a little bit about NASA's Earth Data Cloud. NASA's Earth Data Cloud is the archive of its Earth observations, and it is hosted on Amazon Web Services. The NASA Earth Data Cloud supports NASA's open source science initiative, and it has a lot of advantages. It eases access to data, from different data centers, archived through different data centers, are co-located in the cloud. And it reinforces user data access methods to do data analysis in place and then download outputs. And it also helps toward providing a common suite of NASA Earth data tools and services, and allowing multidisciplinary and multi-mission science. I do want to share that all NASA Earth data does remain free and available publicly. And so all Earth data are available for download. And that workflow is certainly relevant to many researchers. Go ahead and learn more at the website that is provided below. So we are going to work in a Jupyter Hub environment. And if you are a participant and want to follow along live, I invite you now to go to this link. It's called workshop.openscapes.2i2c.cloud. And this is going to spin up a managed cloud service. This is going to allow each participant to have their own managed environment for the notebook tutorial. So if you're at that website, again, it's at the top of the screen there, workshop.openscapes.2i2c.cloud. You'll see the screen grab there and a sign-in. And this sign-in is going to provide you your own environment. Once you're signed in, you will have the capability to choose both the environment and the resource allocation. And so we're going to be using a Python environment, so select Python. And the resource allocation, we recommend choosing, you might need to scroll down a little bit, that is a drop-down, but choose the 29 gigabyte RAM. And once you have that selected, you will have a server that is starting up for you. And this is the part that might take a little while, so this is why we want to get this spinning up now. If you do get an error, just go ahead and keep trying. It's not unusual for a 404 or similar error to pop up, but we do encourage you just to keep trying. And once we get back to the tutorial, we should be ready to roll. Once your environment does spin up, this is what you're going to see. So I just wanted to give a little sneak peek into what your environment will look like, and we'll start there. Now I think we're ready for Satipa.
Thank you, Michelle. So I'm going to present our overview. Invasive species have a massive global impact. Humans and nature are threatened by invasive species across the globe, including threats to ecosystems, the economy, food security, and health. In 2023, the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services produced a comprehensive report on the global impacts of invasive species. The report noted that invasive species are a significant factor that directly or indirectly cause 60% of documented global animal and plant extinctions. It is also estimated that they have an economic impact of over $420 billion. This figure presented in the report shows the distribution of both terrestrial and marine invasive species around the globe. Today's training is going to focus on mapping of invasive species in South Africa. We're going to be using data from the 2023 Bioscape campaign. Bioscape was NASA's first biodiversity field campaign to use airborne remote sensing observations to improve understanding of the drivers and mechanisms behind ecological and biodiversity changes. By incorporating airborne imaging, spectroscopy, LIDAR, and field observations, researchers are utilizing data to better understand South Africa's Greater Cape Floristic region, including surrounding coastal and marine environments. The campaign was organized around three major themes aimed at understanding the distribution and abundance of biodiversity, the role of biodiversity in ecosystem function, and the impacts of biodiversity change on ecosystem services. Overall, this research has a goal of supporting better conserving nature and contributions to society. So the Greater Cape Floristic region is a biodiversity hotspot, with approximately 2/3 of the estimated 9,000 species that grow there being endemic. Most of the region is treeless and is covered in a type of evergreen shrub called fynbos. Non-native trees such as acacia, pine, and eucalyptus have spread into this region, threatening endemic species by competing for water resources. In our Introduction to Invasive Species Monitoring with Remote Sensing webinar, we provided an overview of methods for mapping invasives. Today, we will focus on classification. Classification allows us to visualize differences in spectral signatures to differentiate between surfaces. With enough information, it is sometimes possible to tell the difference between species of plants. Some spectral differences between plant species may be subtle, but are detectable, as illustrated in this figure. Reflectance data is plotted here across wavelengths for a variety of species, and the study is referenced below. For this training, we will specifically be looking at applications of airborne visual, shortwave, and infrared data to assist with species classification. Hyperspectral visible to shortwave infrared imaging spectroscopy data can be used to monitor and measure a wide array of environmental parameters, such as climate variability, land cover distribution, seasonal cycles, and much more. Common sources of this data include ARSET, Next Generation, and PRISM. This visual shows the spectral coverage for a variety of satellites and sensors. ARSET NG has notable continuous coverage across the spectrum. We'll be focusing on it for this training. ARSET stands for Airborne Visible Infrared Imaging Spectrometer, Next Generation, ARSET NG. It was designed with the objective of supporting NASA science and applications by measuring spectra as images that record the interaction of light with matter. These spectra are used to identify, measure, and monitor constituents of the Earth's surface and atmosphere. It is flown on several aircraft platforms listed here and has been flown over places such as North America, Europe, India, and as we have discussed today, South Africa. It has been active since 2009. So ARSET Next Generation has 425 contiguous spectral bands with spectral coverage between 380 to 2,510 nanometers. The spectral resolution is 5 nanometers plus minus 0.5 nanometers, and pixel size is based on altitude. Here are some examples. ARSET Next Generation data can be applied to a variety of studies, including oceanography, snow hydrology, geology, volcanology, soil and land management, atmospheric and aerosol studies, agriculture, and more. An additional example of where ARSET NG data has been used for biodiversity applications is the above campaign. The Arctic Boreal Vulnerability Experiment is a NASA field campaign that was conducted in Alaska and Western Canada as a large-scale study of environmental change and its implications for social ecological systems. Above science objectives were on gaining a better understanding of the vulnerability and resilience of Arctic and boreal ecosystems to environmental change, ultimately providing the scientific basis for informed decision-making. I've mentioned the objectives of the Bioscape campaign, and I'd like to share where you can access data from the Bioscape campaign. So data from Bioscape is hosted on NASA Earth Data, including level 3 data, which we'll be using for the demonstration. You can access the data directly via the links on this page. But if you need a refresher on different data processing levels and the definitions of those, you can find a link here. With that, we're going to switch over to a brief overview on the fundamentals of machine learning for earth science, just so we make sure we're all starting on the same page. So before we get into the demonstration, I'm going to provide a few slides that are from our Fundamentals of Machine Learning for Earth Science webinar series to introduce the concept of machine learning as it is part of our methodology in our mapping exercise. So as we know, the Earth is an intricate and complex system which can be difficult to study. Applying well-known and described mathematical models to the natural environment can be difficult. So machine learning is a tool that can help us understand complex earth science phenomena. Machine learning is a commonly better alternative for nonlinear problems, and a number of researchers have found that machine learning outperforms traditional statistical models in earth science, such as characterizing forest canopy structure, predicting climate-induced range shifts, and delineating geologic facies. There are numerous ways in which machine learning can accelerate scientific research, such as increased efficiency, new insights and discoveries, and improved predictive modeling. Machine learning can help automate the analysis of large and complex data sets, allowing scientists to quickly process and analyze large amounts of data. It can help scientists identify new patterns and relationships in complex data sets, leading to new insights and discoveries. It can also be used to build accurate predictive models that can help scientists better understand complex science phenomena. So here is a general outline of the steps used when applying machine learning. As always, we start with our question or problem statement. We gather data and go through the pre-processing phase. This typically includes things like data cleanup and preparation and is a crucial step. Often it could take much longer than all the other steps, as it helps us understand the data, its patterns, trends, and relationships, as well as detects outliers and anomalies prior to using in our model. We determine our feature of interest and select the appropriate model from here. Now we can go on to training our model, which is essentially connecting our data to an algorithm. This leverages sophisticated mathematical modeling to learn and develop predictions. We can test the model and check its accuracy, and depending on the results, at this point, we may want to reconsider the algorithm we have selected or adjust parameters to improve performance. Ultimately, after iterations, we come to a model with a prediction output we are comfortable using. In machine learning algorithms, there are two broad categories that are most relevant in earth science applications. Those are supervised and unsupervised learning. There is a third category that is also listed here, reinforcement learning, but not commonly used in earth science. You can see in this visual some of the different applications that are used for the different types of algorithms. Supervised learning involves presenting a machine learning algorithm with many examples of input-output pairs, called the training set. It can be further divided according to the type of target that is being learned, as either categorical, so classification, does a given image, for example, does a given image show a star cluster or not, or continuous, which is regression, and an example can be, what is the temperature at a given location on Earth? The model is trained with labeled data sets, which allow the model to learn and grow more accurately over time. Unsupervised learning are not given a particular target. Rather, their task is to learn the natural structure or identify patterns or trends in the dataset without being told what the structure is. Here, the model looks for patterns in unlabeled data. So there are a variety of tools, including coding languages and software packages that can assist us in applying machine learning. This is a nice visual with several represented here, but it's definitely not meant to be comprehensive. Some software tools we will utilize today include the programming language Python, as well as the Jupyter Notebook. Python is a simple, versatile, general-purpose programming language. It is the most used language for machine learning, and it has an active user and extensive library ecosystem to simplify data management and analysis. It is known to be beginner-friendly while still offering advanced users powerful analysis tools. Jupyter Notebook is an open-source web-based application which allows us to create and share documents that contain code, equations, visualizations, and text. Its uses include data cleaning and transformation, statistical modeling, data visualization, machine learning, etc. I'm looking forward to following along in the notebook while Michelle demonstrates for us in just a moment. Due to time constraints, we aren't going to review the intricacies between different algorithms, but if you would like to learn more, I highly encourage you to watch the Fundamentals of Machine Learning for Earth Science training videos. Before we jump into the demo, there are some big questions I would like to present you for consideration as you look into your own applications of machine learning algorithms, such as invasive species mapping. So we always want to consider what is the scientific question we would like to address, and what information are we missing in order to answer this question? What data do we have available? Do we have a training set of data available? What's the structure of our data? Is our dependent variable a continuous or a discrete problem? Are there any performance requirements based on our science question? Is our software going to run locally, on the cloud, or on embedded hardware? And one big thing to consider is what's more important for our project: inference time or model performance. Here on this graph, you can see some of the trade-off between speed and accuracy of some machine learning algorithms. Michelle, I'm going to pass it back to you to lead us through the demo.
Okay, thank you again, Sativa, for that great introduction. We're going to go ahead and jump into the notebook example. During the introduction, we paused for a minute and gave instructions on spinning up a hub environment that I'm showing you now. So if you were successful in spinning this up, you should be here. If you don't see this screen, if you'll just click one of these launcher tabs here, you'll see what I'm seeing here. Sometimes it opens up to a terminal, which I'm going to go to, because the first thing we're going to do is we're going to clone a repository that has the notebooks available, and that will be a repository that will be available after the workshop, so you'll always have access to these notebooks. So I'll go ahead and open a terminal. So this is very much like a command line Unix environment. And we are going to clone the repository that holds the notebook that we're going to run through today. So to do that, we need you, the participant, to go to this website, which is github.com/ORNLDAAC/Airborne. And once you're there, you'll see this repository page. And cloning the notebooks that you see here is relatively straightforward. You'll go to this code block here. Make sure that HTTPS is selected. And you can use this copy link here to copy this URL. Going back to the terminal, we're going to do a very simple git command. We're going to type git, G-I-T, clone, and then we can copy and paste the URL that we just grabbed. Hitting enter on my keyboard, you'll see that that Airborne repository is being copied into my managed environment, which is different from your managed environment. Each participant has their own unique managed environment. So if I make changes to the notebook, they're my changes. If you make changes to the notebook, they're your changes. So you'll see now that you have an Airborne folder showing up in your table of contents. This is what we just copied over. If you double click into Airborne, double click into notebooks, you actually have all of the notebooks that are in that repository for your use. We're going to focus today on the notebook that includes Invasive in its title. So the ARSET Next Gen ARSET NG L3 Invasive Species Notebook is what we're going to be running through. If you'll double click on that, that notebook will open and we can start running it. A little bit of overview to start. As we introduce, this is a notebook that is mapping invasive species using supervised machine learning and the ARSET Next Gen instrument data. This data comes from the Bioscape campaign, which you were provided a lot of information in the introduction. So I'll just welcome you to click on any of these available links for more information. I do want to focus here on the data set that's being used. This tutorial uses ARSET Next Gen Level 3 data set. And this is the citation for that data set and the DOI. So if you click on this DOI, you'll actually go to the landing page for this data set. The ARSET Next Gen Level 3 data is a resampled and mosaic data set. So the surface reflectance data derived from the ARSET Next Gen instrument were resampled to a consistent 5-meter spatial resolution and mosaicked into a regular tile system of 807 tiles. So this gives a level 3 data set, and level 3 data sets are defined here. And there's more information about data processing levels at this link. But level 3 data are variables mapped on a uniform space-time grid, and they're usually complete and consistent, which this data set is. So I want to give credit for this notebook. The contents of this notebook were first presented by a researcher named Glenn Moncrief, who is a spatial data scientist for the Nature Conservancy. Then it was presented at a workshop, an ARSET or an LDAC collaborative workshop, whose information is available at this URL if you want to look at that. Importantly, the content for this notebook has been updated by myself and my colleague Rupesh, so that it is adjusted to access the published Bioscape ARSET Next Gen Level 3 data that are now in NetCDF formats and that are now distributed through the NASA Earth Data website. So at the time of the Cape Town workshop, these data were not available. The tutorial learning objectives are to understand how to inspect and prepare data for machine learning models, how to train and interpret a machine learning model, and how to apply that trained model to ARSET imagery to create alien species maps. So let me go through a little bit, if you're not used to these Jupyter notebooks. There are a couple of ways to run a cell. And let's first start by loading these Python modules. This little triangle button right here will run a cell, and you'll see while it's running, this little asterisk is showing. And once a cell is run, then it will become a numeric number. You can also run a cell just by doing on your computer Shift and Enter. So you'll see me running cells doing Shift Enter and not necessarily coming up here. I also want to note that if your notebook becomes a little bit unresponsive, a couple of things that you can do, and you might see me doing this through the tutorial. You can come up to kernel and you can restart a kernel. You can restart and clear all outputs of a cell, or you can run up to a selected cell. So if your notebook becomes unresponsive, that's a way to manage that. Also, if you go under File and Hub Control Panel, you can actually stop the server and then restart it. And sometimes that's necessary. So as you're doing homework or have access to this hub environment for a couple of weeks after this training, those are ways to get your notebook back to something that's active. A couple of practical details to start. I usually spend more time on this with trainings, but we're going to we're going to use Earth data authentication. So I just want to introduce Earth Access, which is a Python library that simplifies data discovery and access to NASA Earth data by providing an abstraction layer to NASA's APIs. So there's more information on Earth Access. We'll be using it today throughout the notebooks for authentication, search, and access to direct cloud files. So we'll actually run that here by just demonstrating a quick way that we're going to access the bioscape data. I can use Earth Access to search all of NASA Earth data and use the Bioscape project keyword, and you'll see that there are 8 collections found, and I can list those collections. We're going to be accessing this average next-gen level 3 mosaic, and we're going to be accessing it using the DOI. So later on in the tutorial, you'll see us using Earth Access and the DOI for that. Okay, let's jump into our machine learning training then. The first step of machine learning is having data collections and labeling. So we're going to explore a sample land type plot level data that we have. We're using a small data set over the Cape Town Peninsula of South Africa, which is a sub area of where Bioscape had collections. So we have a data set that's already uploaded for you called Cape Town Invasive. It's a geo package. So we're going to first create a data frame to hold the classes that are within that this data set. And you can see that there's a number of land types. Some of them are the invasive types that we're interested. Class 6, for example, is eucalyptus, and class 5 is pine. So we'll go ahead and open that data set. And one thing to note is that this is, again, uploaded for you already in this shared public area in a Bioscape ARSET NextGen Level 3 folder. So we've opened up that geodata package and we're examining the land types and the groups which are important. Let's go ahead and summarize and visualize what is there. So again, you can see the land types and you can see the number of points that have each of those land types. And you can also see the grouping, and the grouping is going to be important in the machine learning because this is dividing our data into training data and test or evaluation data. So that grouping is already available in this data set. And we can also visualize what this data looks like. So you can see the points here across the Cape Peninsula of South Africa. And we have here listed the different land types. So this is a nice interactive way of being able to zoom in and interact with this this data set. Okay, now that we've looked at our plot level training data, we're going to start examining the imaging spectroscopy data. So we're going to log in here and using Earth Access. This jumped me into being authenticated because I already had this netrc file. You will be prompted with a prompt to enter interactively your Earth Data login username and password. And once you do that, you'll be authenticated and you'll be able to access Earth Data. We're now going to search and access the Bioscape ARSET Next Gen Level 3 data. Earlier, I demonstrated that we'll use the DOI from that data set in order to specify which data set we want. We're also going to exclude a GeoJSON file that's in that data set using that wildcard. So you can see with this data set that there are 870 granules that are in the ARSET Next Gen Level 3 data. So let's look at just one of those granules at index 100. You can see that there are 3 data sets associated with the granule. We're interested in this data set, which is the RFL, the reflectance data in a netCDF format. I'm not going to do this, but if you click here, you will actually initiate downloading this data. So you're logged in with your NASA Earth Data login, so you have access to these data now. I don't recommend it, it's a big file. This is a browse image that's associated with this file, and that's also available. Let's take a peek at some of the metadata associated with this granule. And the only reason I want to bring this up right now is because this geometry that's associated is the bounding box of each of the granules, each of the flight lines of the data set that's available. And we're actually going to plot that up in the next step, and that's going to give us a window into the distribution of the data that's available. So let's go ahead and do that. Next step is we're going to create and visualize bounding boxes for the ARSET level 3 files. So again, using that that metadata allows us to be able to do this. So here's a nice plot of all of the data sets, just their bounding boxes right now. But this shows the distribution of all of the tiled ARSET Next Gen data. We're going to focus, oops, I scrolled the wrong way. We're going to subset into this Cape Point region because this is a lot of data. Before we subset that, let's take a look at just one of these ARSET reflectance files. So by using Earth Access, we're going to get direct access to these files on NASA Earth Data Cloud. And you can again see that there's 3 different files associated with the granules. And we're interested and will visualize a netCDF file and a quick look geotiff image. So the next step is that we need to open the file. And you can see that that's open now, and we're provided the URLs for that. And we'll go ahead and separate each of these files into its file type so that we can access them. To open the netCDF reflectance file, we're going to use Xarray, which is a familiar open source project Python package, and it's really powerful in that it is able to recognize dimensions, coordinates, and attributes on top of the raw NumPy-like arrays. We're going to use a Xarray's open data tree, and that's going to accommodate the hierarchical groupings that are in this ARSET NextGen file. And we're going to extract the reflectance file from that. So we'll go ahead and run this cell. And you'll see that the Python package gives us a nice overview of what this data set looks like. So there's 425 wavelengths associated with the ARSET NextGen data, and each of these tiles is divided into 200 by 200 X and Y. So that's a little bit of information on the netCDF structure of these files. Here we're going to plot just the red reflectance. So this takes a minute because we're actually reading the data now, and we're accessing just one wavelength within the 425 bands. We've selected wavelength 660, which is equivalent to a red band. So we'll pause here for a minute and let this read and plot so we can take a look at one of these files. So now we see just one band here, the red reflectance again for the tile that we selected. So now we're actually looking at and visualizing the ARSET NextGen reflectance data. So just to get more of a true color image, we'll take a look at the quick look image, which is actually a 3-band geotiff file. So you can see that's much of a true color image. Now that we've explored the netCDF file structure and accessed those data and visualized it, we'll go ahead and subset those over 800 tiles to just the intersection of the plot data that we looked at earlier. And again, we'll use Earth access and the bounding box parameter to query granules that spatially intersect with the bounding box of that plot data or the class data. So we'll go ahead and run this cell that searches for that, and then we can plot that up. Again, just the bounding boxes are plotted here, but it gives you an idea of each of the netCDF files that intersects the plot data over the Cape Peninsula. The next step is to extract spectra for each of the land plots that we have. So we're familiar with the data, and we want to get the average spectral data at each label location. And the function below is going to do this, and it's going to return the results as an Xarray. So we'll go ahead and run that. You'll see that the asterisk is still here, indicating that this is still running. And you'll see that this is stepping through each of the tiles that we provided above that are over the Cape Town area. And it's extracting the points that intersect with each of those tiles. So the first tile had 40 points in it. The first data set had 40 points in it. And this is extracting for each point, it's extracting the 425 band spectra for each of those points. So we'll go ahead and let that run through each of the tiles that we have from above. It's fun to watch it run through and to see the number of points that are within each of these data sets. So we're concatenating all of these spectral profiles into this ds_all file, and we can take a look at that. So you can see there's 319 points that we had, the land class points, and of course the wavelengths of the average data. There's 425 points. We're going to clean up this dimension, this file dimension isn't needed, and we're going to do that with a helper function that we have included in the repo. So you can see we're now down to the 319 plots and the 425 wavelengths. Now that we have the spectra, what we need to do is merge the point data and include the labels class and group that we shared earlier. So recall class is the equivalent of a land cover type, and the grouping is the training versus the evaluation data. So we'll go ahead and run that. And we've defined all of the operators that we want, but Xarray has lazy computation, meaning that we haven't forced these calculations and we have not stored them into memory. And so that's the next step. This step takes a little bit of time, so we've commented it out, but it is available here for you to run on your own if you want to. Because we're not running this, we have also included the data here in the shared public area. So it's output as this dsp.nc file. Okay, so now we've got this data into memory and we can start working with it. So I just want to quickly, I do this a few times throughout the workbook just for recall. Remember, class 6 is our invasive species. We're going to focus on the eucalyptus in this notebook. So for class 6, what we're going to now do is we're going to plot the spectral profile that's been extracted for each of those points that are eucalyptus for class 6. So here you can see for all of the points that were labeled eucalyptus, this is the spectral profile for each of those plots that we just extracted. So just to step back and say and share, at this point, if this is demonstrative of a machine learning workflow and certainly one that you can apply, but at this point, you should closely inspect the spectra that you have for each class. And we can change the class that we're looking at just by changing the class value here. If you wanted to look at water, you could change that to 8 and rerun that cell. Okay, the next step is to prep the spectral data for the machine learning model. So, of course, part of prepping for a machine learning model is to make sure our data are in good shape. A couple of things we're going to do is we're going to drop bad wavelengths, which is very common for these types of data, to drop the atmospheric windows and typically the bands on the edges. And then we're also going to normalize the data. So this first code block simply identifies wavelengths to drop and applies that, and you can see that we're now down to 325 wavelengths. And then the next thing we're going to do is we're going to normalize the data. And there are a number of different ways to normalize data in a machine learning workflow. We're just going to do a brightness normalization. And in that, we're going to scale the reflectance of each wavelength by the total brightness of the spectrum. So we'll go ahead and run that. And then again, for the same class 6, the eucalyptus, we'll look at those normalized spectra. And you can see that as they're normalized, that some of the variance in those spectra profiles for each of the plots is more normalized. Okay, well, congratulations. We have collected and labeled spectra data for each plot location, and we're now going to train and evaluate a machine learning model with that. So the machine learning model that we're going to use in this example is called XGBoost. XGBoost is extreme gradient boosting. It's a class of models that is related to random forests. It's a little different than a random forest because gradient boosted trees differ in that they build trees sequentially, and each new tree is focusing on correcting the errors of the previous tree. And this sequential approach allows XGBoost to create more accurate models by iteratively refining predictions and addressing the weaknesses of earlier trees. So here we're just importing libraries that we will use, the Python libraries. And just to recall that we have already divided our training data into training, which is labeled number 1, and test or evaluation, which is labeled number 2. The next step is we'll separate the data into training and evaluation subsets for this model training and evaluation respectively. So we have the training data set, the evaluation or testing data set, and then the variable classes that are extracted from both the training and the testing data sets. So we'll go ahead and run that cell. So now we're going to train the machine learning model. And the steps that we're going to go through are below in the next code block. But just to go through about what that code block does is we'll define the hyperparameter grid, and then we'll create the XGBoost classifier object. And then there's more information here about setting up the grid search CV object, setting up the grid search and fitting the CV object to our training data. And once the grid search completes, we'll print out the best set of the hyperparameters and the corresponding best score. There's more information here for you to take a look at. Go ahead and run this cell. Okay, and you can see that we have printed out some of these results. We've defined the learning rate, the maximum depth, and so on in the parameter grid. And then you can see that our best score is about 64%. There are a few ways to evaluate the model performance. You can see that we have this object now called best model. So we'll use best model to predict the classes of the test data. And we'll calculate the F1 score, which is sort of a balance between the precision and the recall, and evaluate our overall performance. So assessing the precision, which kind of answers the question of all the instances that we labeled. For example, eucalyptus, you can walk through each of the classes, but we're going to focus on the invasive species. How many were actually eucalyptus? And then recall answers the question of all the actual eucalyptus, how many did we identify correctly? So again, we're using this the best model to evaluate the model performance. So we'll go ahead and look at each of these steps. The step to calculate the accuracy and the F1 score, and then we calculate the precision and the recall for class 6, and print that out, and then we'll actually plot a confusion matrix. We'll go ahead and run that cell. So you can see that our accuracy is 66, which provides a general measure of how well the classifier performs overall. The F1 score is about the same, about 66%. The precision, again, measuring the proportion of true positive predictions relative to the total predictive positives for a class. And then the recall for the class, for class 6, which is the eucalyptus class, is about 71%. And then the confusion matrix, which is printed here for all of the classes that we're modeling today, the predicted label versus the true label, and most most mostly we'll look at this diagonal, and that gives us an idea of how well each class is performing. All right, so again, I want to remind us of the land color types and cover types. And once we have our model trained, we want to step back and look at and interpret and understand the results of the model. And there's we'll share a couple of ways to do that. Um, but it is crucial for understanding how models are making predictions to interpret the outputs. And one way to do that is with this SHAP scores, and this is a popular method for interpreting model predictions. So SHAP scores explain the contribution of each feature. In our case, it's the wavelength. There's a lot of wavelengths to take into account, but we'll look at the wavelengths that contribute highly to each of the class predictions. So each SHAP calculates how much the prediction changes when the feature is included compared to when it is not, considering all the possible combinations of features. So let's go ahead and initialize that, and then we have a couple of ways of actually visualizing these SHAP predictions. One is called a force plot, where we can see an individual prediction to inspect how the input features have influenced its assignment to a class. So if we look at the 55th prediction, we can see that the predicted class was eucalyptus and the true class was eucalyptus. So that predicted and true class were actually the same. And we can see in this force plot the individual wavelengths that have contributed positively and in a lower way, which is the blue score. So we have a note here that features pushing the prediction higher are shown in red, and those pushing the prediction lower are in blue. So these red wavelengths were very instrumental in that prediction. We can look at another individual prediction. In this case, the predicted class was forest, but the actual true class was pine. So if you look at the forcing plot for that, you can see that the blue scores are contributing to the lower predictions for that particular plot. A bee swarm is another way to look at these data. And this actually, I'm going to go back to class 55, which was the eucalyptus plot that both the predicted class and the true class were eucalyptus. And so this provides us with the wavelengths, but also a look at the feature values from low to high and the impact that each of the predictors had in evaluating that. So this is a way to look at individual plots and their contribution. And then finally, we'll overlay the actual spectra for an individual observation to understand how spectral features are contributing to this prediction. So we'll go ahead and run this and look at what we mean by that. So here we're able to, for that prediction, look at the actual spectral profile, and then the importance of each of the individual wavelengths are plotted, and the darker the color, the higher the importance of that wavelength. So this is a nice visualization for that. And then the next step, of course, is to deploy the model that we have trained now to the ARSET scenes. So taking that trained model now and applying it to each of the ARSET scenes that we looked at above. The first thing we're going to do is we're actually going to limit these predictions across the ARSET scenes to just the natural areas. So I'm going to step back a minute and introduce another data set that's loaded into that shared public area that is going to limit the predictions to natural areas. And so let me zoom in here to our Cape Town Peninsula study site, and we're actually going to mask to this national park area. So we'll avoid the areas that are in natural areas. And then to do that, we'll also want to limit the ARSET scenes, the ARSET data, the level 3 data, just to those natural areas. So again, just plotting out the bounding boxes of that data that we're actually going to analyze. Okay, so let's predict over just one ARSET scene to start. So stepping back, we have our trained model and we're ready to deploy that to generate predictions over an entire ARSET scene to look at the distribution of invasive plants, but also the distribution of all of the 9 classes that we have. So this is big data, and the first step here allows us to optimize the way that those data are being analyzed. And then we'll jump into the actual function here that is doing the prediction. And that's divided into 4 steps. And we won't, for the sake of time, I won't read through the 4 steps. There's a lot of kind of unpacking the data and repacking the data that's necessary in order to run it through this particular machine learning model. And that's described here and also defined in this function. So we'll go ahead and run that function. And I just want to show that that has run. And then we'll go ahead and run that on just one single file. And we want to do that before we run it through each of the files that we're going to ask it to run. So you'll see that that we're now running this prediction over the entire ARSET scene here. This is the particular scene that we're running it on. And you can see that we have the 9 classes that we're predicting over, and then the 2000 by 2000 XY. I'll skip that cell. That's just again sharing the labels. But now we're actually going to plot out our prediction over the entire tile. This does take a minute to run because we're extracting now class 6 from this large netcdf file. So we're just going to look at class 6, the eucalyptus class, and see what the predictions are for this particular class. So while this is running, we'll just look at this next block of Markdown that, machine learning models typically provide a single prediction of most likely outcomes. So you get a probability-like score that ranges from 0 to 1 from these models, but don't think of these as true probabilities. And we'll see this in the mapping. So if, for example, the model score is 0.6, that means that it's more likely than a 0.5 prediction, less likely than a 0.7. But it doesn't mean that your prediction is right, 6 out of 10 times or 60 out of 100 times. And there's some information here if you want to dig into it, that shares a paper that discusses how to get to a model's true uncertainty using a technique called conformal predictions. So the reference to that paper is provided there. And once we have this output from one tile, the next thing we'll do is we'll show how this loops through each of the ARSET next generation tiles. And we have output for the entire peninsula that we'll take a look at. Okay, hopefully that was worth the wait. I think so. All right, so we can see that we have a probability map here. Let me get that in full screen. So here's our class 6 eucalyptus probability mapping across the entire scene, but also masked out to just the natural areas that we shared earlier. So the probability mapping, you can see that there's a range from low to high, and you can see that the eucalyptus areas are mapped out. You can run this for each of the classes, and you can see that the probability is ranging from a low probability, but that there is a probability up to a high probability for eucalyptus. Now that we've run that for one tile, we can loop through each of the tiles that we identified earlier. And these are the tiles again that that intersected with the natural areas of the Cape Town Peninsula areas. What we're seeing now is that it's run through one of the tiles. It's going to run through all, I think there are 9 or 10 tiles that it'll run through and do the classification for. Okay, we can see that the asterisk has gone away and we have the code block number here. So this block is finished. And again, this looped through each of the ARSET level 3 tiles and performed the calculation, the computation, the prediction across each of those tiles. So you can see the listing of the tiles that are in the Cape Peninsula that had area in the natural area. So we have results and we want to look at those. So to do that, the next step is to merge and mosaic results. So we have them now available as a list of X-arrays, one for each scene. So we'll want to combine these together into a single seamless mosaic for the entire Cape Peninsula. So fortunately, Rio X-array has a mosaic function that will go ahead and do that in a simple way for us. So we've imported that. The next code block is one that does take a very long time to run. And so we're not going to run it here during the demonstration, but we do have the code for you. And we're outputting the data as a TIFF file. And so the advantage of doing the work in the cloud and using that resource is evident here in that once you have that TIFF file, you can then download that TIFF file and use that in perhaps another level of analysis that you would want to. We have a note here that we're using a lot of resources, that it might be beneficial to restart the kernel. Everything's been running great, so I'm not going to worry about that. But what we're going to do is go ahead and probably just re-imported libraries that we've already imported, but just to make sure. But the next thing we'll do is we'll go ahead and look at or open up the results of the predictions for the entire Cape Peninsula as that GeoTIFF file. And again, we've run that, we did the mosaic and the merge, and we have that stored in that shared area. And finally, let's plot this up. Let's take a look. So we're looking at band 6, which again is the eucalyptus, that invasive species that is found across the Cape Peninsula, and looking at the probability mapping based on this machine learning and the training data that we provided. So this is the probability mapping of class 6, which is the eucalyptus class, over the entire Cape Peninsula, having merged each of those 9 or 10 different ARSET next-gen scenes, and also masked just 2 natural areas. So each of these classes is available in the GeoTIFF file that we have uploaded. And that is the result then of applying our machine learning model to each of the ARSET scenes across the Cape Peninsula. So just a final note that we'll want to inspect these results. We want to decide where they look good, where they don't look good, and think about if our workflow needs to be refined. And importantly, looking at our training data and how that affects our outputs. So again, I want to just give credit to Glenn Moncrief, who originally shared this at Bioscape Workshop. I want to thank my colleague Rupesh, and he and I worked together to update this to the current distribution of ARSET next-gen level 3 data and the NetCDF file formats. And I hope that you all have had a window into some image spectroscopy and some machine learning to map invasive species. And a final note is that this entire notebook and the recording will be available the day after the training workshop, and the hub will remain available for until October 14th. So that if processes are slow, if a lot of people are hitting the hub during the training, don't worry, you'll have access to it, and you can have the time to wait for processes to run, and maybe during times when we don't have such heavy usage with all of the participants logged in. So thank you very much. I'll turn it back over to ARSET to close us out.
Thank you so much for that demonstration, Michelle. So I'm just going to close this out, and just a reminder of some of the considerations that you may want to consider when undertaking a remote sensing approach to monitoring invasives. There are, always going to be factors that are unique to your situation, to your study, but some general things to keep in consideration are things such as cost. That could be for, compute resources necessary, actually collecting the data, Always be wary of scale mismatch for the question that you have in mind. What temporal resolution is available for the data that you can access? What is the range of spectral signatures that you need in order to answer the questions you have? Again, the general idea of availability, is this data available in your area of interest, and always complexity, how long is it going to take to process and analyze the data, and is it within your bandwidth to proceed with this type of analyses. And in summary, we provided an overview of the impacts of invasives and introduced the Bioscape campaign. We highlighted Airborne Visible Infrared Imaging Spectrometer Next Generation for biodiversity applications and data. We used a Jupyter Notebook to access ARSET data located on the Earth Data Cloud. We demonstrated the classification of invasive species using a machine learning model for the Greater Cape Floristic region in South Africa. We discussed how image classification of airborne imaging spectroscopy and labeled field data can be used to map invasive species, and reviewed key considerations for interpreting machine learning end products for invasive species mapping and land management decisions. So a reminder, there is one homework assignment. It's going to open later today, and you can access it from the training page. You must submit your responses via Google Forms and turn this in by the 14th of October. You will need this in order to receive a certificate of completion. You also would have needed to attend the live webinar, and you will receive your certificate via email approximately 2 months after the completion of the course. Here is some contact information for myself and the rest of the ecological conservation team. There's also a link here to our website, our YouTube, and we have an email for general inquiries, comments, etc., arset@gmail.com. We encourage you to join our quarterly newsletter so you can stay up to date on our latest trainings. Here is a list of resources that you can use to supplement your learning. Thank you so much. And with that, we are going to go into the live Q&A. We appreciate you all sticking with us to the very end. Just a reminder, if you have any questions, you will go ahead and type those in the Q&A portion there at the bottom of the screen. If you click those 3 little dots, it should bring up the Q&A portion. So I'm going to invite Michelle and Rupesh here to assist in answering the questions that you all have already submitted. The first being, if there is a way to change resource allocation once you're in the hub. And there are some instructions here for you on the screen. So if you go to File, Hub Control Panel, Stop My Server, Start My Server, you should be able to see the options for environment and resource allocation again, and you can just update that for the specifications you need. Great. So Michelle and Rupesh, thank you again. We really, appreciate you being here to share your expertise and provide this incredible demo. One of the questions that the group has, if there are any labels available for this data in order to train supervised models. So yeah, I have here a note that hopefully this question was answered in the training, and that we are using the class labels to train XGBoost. Those labels are what you would use in any other supervised classification model. Thank you, team, for getting those responses typed out for us. Okay, and then there was a question about why the GeoJSON file is excluded. Michelle, we have here noted that it's only used to provide the tile footprint and it isn't an image. Is there anything else that you would like to add here?
Hi, Sativa. No, if you look at all of the data provided with that data set, or sometimes we say collection, we did create a GeoJSON file of the footprints of the tile data. Just for sort of an ancillary file to be able to view, um, where the tile data are, much like what we did when we plotted up all of the bounding boxes. So we just didn't want to, we were focused in on the ARSET next gen data and not that GeoJSON file. That was the only reason to exclude it, but it is available in the data set.
Thank you, Michelle. It looks like we had a participant who had some issues on line 13 with accessing the .gpk data, and they got a code block saying that data was not found. There was a suggestion here, and hopefully these instructions could help resolve the issue. So yeah, try using this path here, and it won't work if you place your notebooks in a different folder. So just make sure everything is located in the correct path that you are referencing. There was a question about data being available for other locations globally. So this data specifically was collected for the Bioscape campaign in South Africa. So it is a sensor that was placed on a plane, and that data was gathered for a specific point in time in 2023 in October and November, I believe. So there is other ARSET data available. Of course, your availability will be limited temporally and spatially, just depending on where these campaigns exist. So there's no global coverage. We don't have something, a plane flying consistently to gather this data in the same way that we have for this training. But there are hyperspectral satellite-based sensors at lower spatial resolution that you can check out. And there's also a comprehensive list of the ARSET next-gen data that can be found at the link here. And just a reminder that this Q&A will be posted to the training website for your reference. So you will have access to all of these links. Okay, the next question is, can you please recommend resources that will help in understanding the code and the overall idea of analyzing satellite data? I see the team has put some links here to the GitHub for the ORNL DAC, as well as NASA OpenScapes and Earth Data. Is there anything else that Rupesh or Michelle you'd like to share as far as the methodology you provided for us today?
Well, what a great question. There are many resources that the data centers are creating, much like this, and have available on Earth Data, NASA Earth Data, and OpenScapes is a group where many data center representatives get together and create content to help users to learn about cloud access, but also give more in-depth tutorials for analyzing, in our case, these airborne data resources, but also some other satellite data. And I will add another one to that list that is specific to an instrument that is very similar to the ARSET data we just looked at, but it is on the International Space Station. So it's more orbital and has more coverage. It has lower spatial resolution, of course, as Sativa said, but it's called EMIT, E-M-I-T. And there are a lot of resources available to analyze those data. And that one comes to mind. There are others. And I'll find a link for EMIT and other Earth data tutorials.
Thank you, Michelle. So the next question is asking if this cloud service will be available for future use, and how can we find hyperspectral imagery for other regions of the world and follow this workflow? So just to note that this virtual environment was set up specifically for participants in this training. So you will have access to the cloud computing for about 2 weeks in order for you to work through the notebook at your pace, right? I'm sure some of you, weren't able to completely run through it live, which is totally fine, which is why we have it open. It's also a place for you to be able to reference as you complete your homework assignment. So unfortunately, after that, it will be closed, but you can still get NASA Earth observation data for areas around the globe, and the link is here. So you can use Python Earth Access for module for searching programmatically. So you can access Earth data through Python in order to move forward with other analyses. And although airborne coverage may be limited, as Michelle referenced, we have some hyperspectral data from emit that could be a resource. So yeah, unfortunately, the virtual environment is specific to our time together, but it could be something that you consider as a resource for your own applications and seeing what kind of cloud computing you might be able to access through your own organizations and institutions. All right, so the next question is, was this just for one time period, or did we load up a whole chunk of time series for the available data? So the data set that we use was created using flights for the time period of October 22nd, 2023 through November 26th, 2023. And the source for that data is linked here. Okay, the next question is a really interesting question. How much does it generally cost to initiate an ARSET next-gen project in an area that hasn't already been covered? How much extra does it cost to get level 3 data? And does that depend entirely upon the size of the project? Yeah, so I mean, I would love if anybody else could chime in with specifics here. But so AVRIS itself is usually flown for NASA-funded projects. Maybe you can apply for something like a ROSES solicitation, which is NASA-funded research. And if you have research ideas yourselves, you could look at the NSPIRES link here, which regularly announces funding opportunities. But I don't know if anybody on the call has an estimate for what some of those costs are for an AVRIS campaign.
Yeah, that's a great question, Sativa. I don't know either. And so I will. So just a reminder that Avarice, Next Gen, and 3 other airborne instruments were flown during the Bioscape campaign. And we provided links to some of the website information with Bioscape, and that was NASA's first biodiversity campaign. So it's a pretty cool area and a pretty unique campaign. And so that was part of a NASA funded project. And so, the PIs who proposed to that would have, during that process, requested those facility instruments. Facility instruments are typically are instruments that, as PIs are proposing that they would request through the NASA Airborne Science Program to use those instruments and coordinate with those programs to have those flights and the data provided. So it's very much wrapped in with those proposals. And I'll just add that those instruments are often flown with NASA campaigns, but they will also fly to support other activities outside of, of even NASA. So it's not just specific to NASA.
Okay, the next question is asking if we can identify the labeled AVRIS next-gen data set for species. So I'm not sure if this is referring to the data within the notebook itself or generally. Any insight there, Michelle?
So the data that we used in the notebook are available in the shared area. Um, and that data was part of the Bioscape workshop that we did in Cape Town. So we used that. There, you know, that's a great question, and the for anyone's sort of area of interest, obvious, you know, there's a lot of effort that is required to do those sorts of field observations and have those types of training data available. And so it would be something that would be unique to somebody's area of interest if they have those data or if they would need to access those data. If so, there is Bioscape data that is posted through NASA Earth Data, and it's not yet published, but there will be more field data that was collected during the Bioscape campaign that covers a broader region than that Cape Town area. So if you check back to the Bioscape project on NASA Earth Data, those data will become available once the PIs are ready to publish those data.
Awesome. The next question is about the minimum size for an area of interest in order to apply this approach and be effective. This is specifically for someone who comes from a smaller community looking to track the spread of a certain invasive plant, but not sure if there's enough area to provide enough training. Yeah, so if there is AVRIS data available for your location, we did reference the pixel sizes that would be produced. So that if you want to reference the slideshow, so we could say at about 18-meter resolution, which is pretty fine in scale. So we would think that it could work for a smaller training data sets as long as the data sets are spatially distributed across ecosystem and vegetation communities that you have of interest. So yeah, if the AVRIS data is available, it's at a pretty fine scale. If AVRIS data is not available, then it's just a matter of what is the spatial resolution available for the data that does cover your area of interest.
Sativa, I'll jump in also.
Yeah.
So when we cloned the repository, there were several notebooks, and one of the notebooks is called AVRIS Search and Discovery. So first of all, we're talking about AVRIS data, but the techniques in that search and discovery notebook can be applied to any data that is any NASA Earth data that's published to look both spatially and temporally for what data are in my study area. And the NASA Earth data has tens of thousands of data sets, and so take a look at that notebook, and you'll have to extrapolate a little bit if you want to look for data outside of AVRIS, but you can that goes into some details using NASA Earth Access like we did today to look at to be able to search for Earth data. There's also just a wonderful UI on NASA Earth data. It's called Earth Data Search. And you can, using that GUI interface, you can put in a spatial area of interest and a time series of interest to see what over all of the NASA data, what data might be available. And you'll want to filter by project or instrument, as you do that to narrow your search. Otherwise, you'll get a lot of data because of all of the orbital data that's global. But yeah, take a look at that notebook if you're interested in programmatically trying to search data, NASA Earth data, or just go to the Earth data search GUI, and that's a wonderful application for searching data.
Thank you, Michelle. So the next question is about tracking invasive animals. Animals move around, so it is a little more difficult to use remote sensing for the tracking of animals, but we did have an introductory training to animal tracking earlier this year that if this is a topic of interest, I highly suggest that you check out. There's some pretty interesting techniques being utilized in order to track invasive animals. One thing to note is that if an animal could leave a mark in their environment, such as an invasive pest, which causes damage to a specific plant species, this could be a way to, kind of note where this pest has been. Also things just general like habitat mapping and the suitability for different species to probably be in an area is another way to think about it. So is the habitat suitable for that particular invasive animal to move to? And so anyway, again, this is a little more difficult because we just have timestamps from our remote sensing, but there are some creative ways that researchers are tracking animals and using remote sensing to support that. So check out the training on tracking of animals. The next question is asking what approach would be good to auto-label some of the data to get more training data. So the note here is you can probably use some auto-labeling, but this training data was collected using manual labeling. Just a different way. Anything else anyone would like to add there?
Yeah, that's a good question, Sativa, and that what you said is correct. That was field data that was collected, and so if you thought you needed more training data, I think heading back out to the field is within the scope of what we presented here, is to just get more field data.
Thank you. We had a lot of participants from India. I was noting where people were coming from as they entered the chat. And the question that we have next is, how much data is available for the Indian region? And cool thing is ARSET 3 is planned for India later this year. There'll be a campaign. So you could check out the link to get more information.
Yeah, Sativa, I'll add that there have been other ARSET campaigns in India. So again, go to the Earth Data Search UI and search over that spatial area and filter your search to ARSET data, and hopefully that will help you to discover those data.
You. Okay, so the next question is asking about for more explanation on the tuning parameters we use for XGBoost. That's a little bit out of the scope of this Q&A session itself. It'll take quite a bit of time in space, so we suggest you look at some other online resources, and we have a document listed here that you can refer to.
Yeah, and I'll just pop in here. This is Justin. To say that the important thing to take away from this is that this example used a grid search to minimize the loss function. There are other ways of going about that, but a really nice way to get comfortable with XGBoost and how it works is to manually try tuning some of these parameters and seeing how it changes your model.
Thank you, Justin. All right, let's see what we have next. Okay, we have a question. Is it possible to spectrally super resolve one hyperspectral image, for example, 10 broad bands to 100 bands by considering the nanometer interval? I am not sure I quite understand this question. I think I'm going to leave this one here, and we can put our brains amongst the group and see if we have a response that we can provide you later on this document. Thank you for your question. So the next question is, are there any open source spectral libraries other than USGS, ASTER, etc., for invasive species? So in addition to NASA Earth data, there are openly available spectral libraries. And here is a link to the ECOSIS organization website. Okay, so can I get a note how much longer we have for the Q&A from anyone online? Just so I know how much more of these we're gonna be able to get through.
Except the next one, we have about 15 minutes.
Oh, okay, great. We have plenty of time. So let's see what we have next. Okay, so I'm gonna skip over to question 19. So can I use the SAM with some threshold limit to filter the spectral signatures to make the training data for training DL models? How can I set the threshold values for SAM? So a note here is you should be able to use SAM to threshold limit. The threshold values will probably need some testing based on the area of interest. Would anyone online like to add more to this?
Yeah, I'll hop in to say that this the answer to this question falls in the category of questions we get a lot, which is it really depends on what it is you're trying to study. So it's best to think about your end goals first and then work backwards to think about the best method to get you there. This would be different if you're looking at something like herbaceous vegetation that doesn't have a lot of spectral differentiation from the surroundings. Would be different if you do have like that high spectral variability. So it's not a satisfying answer, but it depends is the best I can do.
Thank you, Justin. The next question is, can this methodology be applied to data from hyperspectral satellite sensors? What would be recommended sensors and how would the spatial scale change? What about SAR and optical data? Great questions. So we've mentioned EMET a few times during this Q&A, so that could be one place to start. We haven't personally went through this workflow with SAR optical data, but you have the foundation with the code in order to start and see if it is a viable method for your areas of interest. Maybe you can get back to us if you produce a case study of your own that you'd like to share.
So Tiva, I'm going to jump in. I don't have edit access, but the other satellite mission that is relevant to terrestrial applications is PACE, P-A-C-E. So that is another good instrument. There are also several European instruments that are not available through NASA Earth data, but there are other satellites that could be helpful. And then if we jump back up to question 18, I want to point out a NASA campaign that was very specific to that question, and it's a campaign or a project called SHIFT, and that's SHIFT. And if you'll there's a lot of data that's published around the Shift campaign, and the purpose of that campaign was actually to get a pretty dense temporal period of average data to look at the phenology over growing season. So check out that campaign, and there's a lot of formal journal publications from the science team that were part of that campaign.
Thank you, Michelle. And just a little bit of something to look forward to is we may be highlighting the SHIFT campaign in a future ecological conservation training. So make sure that you're signed up for the listserv so you know what trainings ARSET's offering. And yeah, for you who asked this question specifically, that might be a place to get some more information. All right, so we will go to question 21. And the question is, can I use the spectra of the species which were collected for a US species to study the same species grown in India with the available ARSET data? And specifically referencing the ISRO campaign of 2015, 16, and 18. So I'm not familiar with these campaigns, this data set specifically. Anyone on the call have more information, or is this something maybe we can look into?
Yeah, I'm not sure if this has been done, so I won't state this authoritatively, but using the spectra of known species, if they are the same species growing in India, does make sense to me. The spectra shouldn't change species to species very much, so I think you should still be able to extract useful classification information.
Great, thank you, Justin. The next question is asking if this workflow and notebook could potentially be adapted for UAS imagery. And this participant specifically has a 5-band multispectral camera and would be working with low spectral resolution, but high spatial resolutions.
Yeah, I'll hop back in here and say that if you have that high spatial resolution, you might be looking at something like segmentation to actually look at the shape of the target species to make up for the low spectral resolution. With only 5 bands, you're only getting 5 data points, so a lot of things look very similar. You're going to miss a lot of the detail in between those spectral bands. So use a method that's going to leverage your high spatial resolution rather than relying on the 5 bands.
Yeah, and do you think it would be okay to say here if you identify a remote sensing data set that can kind of, complement your analysis here, that might be something that is a resource, right? So maybe not the same in the spatial resolution, but can definitely provide that background information on the spectral resolution side.
Yeah, absolutely. If you've got a hyperspectral overpass around the same time, or you can be reasonably certain that things haven't moved, then you could probably bridge the gap between your high spatial resolution, low spectral resolution, and the hyperspectral overpass using your UAS imagery as sort of a ground truthing.
It looks like we have just one more question. These have been really great. Thank you all for your thoughtful questions and engagement in this training. So to our final question is, when applying the machine learning training model, do you need to mask the training plots so you are only classifying test/evaluation pixels?
So we masked. So in the tutorial, we didn't necessarily mask to the training plots, but we did select ARSET data that were over the training plots. And then we applied a mask that limited the classification or the projections just to natural areas. And so I think that's cleaner. Otherwise it would be projecting over, urban areas and areas that aren't natural areas. And you would get an answer. So you don't have to apply that mask. But I think it did help to refine the results to something more meaningful. So I hope that answered the question.
I'll just add that
Yeah.
for XGBoost, when properly configured, it should be fairly robust overfitting. So if the area you're doing your classification over is significantly larger than the number of test plots you have, you shouldn't have to worry too much about predicting on your training data. So you should be able to reuse that. And this is just down to the structure of the gradient boosting tree. So it's this tree approach that makes XGBoost particularly robust to overfitting.
Wonderful. It looks like one more question popped up in the chat, and we got to get that over to the Q&A document. This is a really interesting question. So it's asking about the possibility of creating 3D models using the overlap of ARSET's next-gen data. So the question being, can 3D canopy models be generated for individual species? I'm gonna just speak here again, on intuition of, the species level is something that's very difficult to do, even with the spatial resolution that is provided by ARSET data. This really, takes like some pretty intimate knowledge of your area of interest and could potentially be modeled with, knowledge, like on the ground knowledge of individual species, locations. I'm wondering, I'm thinking about, LiDAR data and JEDI comes to mind, but the resolution's quite large. So again, that species level detail is hard to get at. But I'm wondering, anyone else on the call, what insights you all have about this question? I think it's really interesting.
Yeah, Sativa, that's a great answer. I'll also share that one of the other instruments that flew during the Bioscape campaign was Elvis, and that is not the rock and roll singer Elvis, but it's LVIS, and that's a full form LiDAR instrument. And so those data are public. And if you need help finding it, just let us know and we'll point you to it. But there is some kind of structural data that's available with the Bioscape campaign, and like Sativa said, getting at that kind of vegetation structure, having those LiDAR data was the purpose for that. Great question.
Well, again, thank you all for being here. Thank you, Michelle, Rupesh, and all of the ARSET family for hosting this webinar, for providing some really insightful responses. And just a reminder, please complete your homework and get that done before October 14th in order to receive a certificate of completion. All materials will be posted to the training website within 48 hours. And we are offering a second repeat of this training in just a little while. So there may be some more Q&A questions added to this document or a separate one, but suggest you go there as well and check out what the rest of the community is asking. So with that, we will close out. I hope you all have a wonderful rest of your day wherever you are located in the world. And please come back and spend some time with us in a future training. Take care, everyone.